Perfect. Okay, yeah, again, thanks for the introduction. And today I'm going to talk about my research topic here at the University of Science and Technology in Norway. And what I'm going to talk about today is realistic face anonymization. This all started during my master thesis about 3 years ago and ended up being also my PhD work. And what you can see on the bottom screen here is how this system works. It takes a face and then it tries to generate something that looks realistic, but is anonymized. All of this work is open source, so you can check out the code and try it out yourself at the URL linked here. This all started by me joining the computer vision group, researching on autonomous vehicles here at the university. And we were 3 years ago, a group of 13 students working on computer vision research in Nordic areas. So pretty much what challenges are special for the Nordic climate that we live in. One of the challenges that we had when we first started is that most of the open source data that we have is mostly collected in the US or in Germany. And the driving climates there are quite different from what we can see in the winter in Norway. So the main motivation behind this work is that we want to collect data in Trondheim such that we can specialize into Nordic environments. Now, if I want to start record, or if I start to record data in Trondheim and on the street, I'm going to collect a lot of personal data. I'm going to take it to the streets of London here. And if I now record data here, you see that I'm capturing a lot of personal data, mainly faces, but also license plates. To freely collect this, I am required by GDPR to anonymize it. The actual anonymization is not that hard, and there has been techniques for this for a long time. You can just anonymize it by pixelation or blurring. But in the for a human being, it's very easy to see that this data is corrupted. And if we want to do computer vision research based on this data, I'm not able to reuse, or I'm not able to ensure that my results are the same as with non-anonymized data. But if we're able to realistically anonymize it, I should be able to freely use the data for computer vision research and collect it without breaking the privacy regulations in Europe. These are the results that we currently have with deep privacy. And you can see a little bit of flickering, but it looks somewhat realistic. Now, the way this system works, and I usually present for Norwegians, and for those who don't know, this is the Norwegian government. The way the system works is that we're first doing face detection, then we're doing pose estimation to guide the generative process. And when we have this information, we can remove everything that we consider is breaking the privacy of individuals. In this case, we're focusing on the rectangular area of the face. We just straight up remove it, and then try to generate something that looks realistic. And the results of the system you can see right here. Going back again to the original image and the anonymized image. Now, the architecture of deep privacy is this two-stage model. The first stage is the detection phase, where we're doing simultaneously face and pose estimation. When we have this information, we take a clip out of the face region, and then we anonymize them individually. So we're taking just one image crop at a time and then passing this through what is called a generative model. Face detection is quite easy, or there exist methods that achieve almost 99% recall on faces. And pose estimation is also very good at this stage. However, generative models for face anonymizations haven't really been up to the task or at least before this work. The way the generative model works, and this is also the main topic of my research, is that it takes the face with the certain area masked out, and then also the pose of the face. And then this is passed through what we call a generator. And then the generator is just a straight up convolutional neural network in this case. And then we process this and you get out a face or an painting of the conditional information. So on the left-hand side, we have the conditional information, and on the right-hand side, you have the generated face. Now, the question remains, how do we actually train this generator? If I initialize this generator to, or this convolutional net to random values, it's going to just output garbage. But we have to train it somehow, and what is required then is an objective function. And I'm going to go over generative modeling very, very quick. This might be a recap for anybody that has taken an AI course or a pattern recognition course. But generative modeling is the task. So you have a set of training samples that defines your training data. And the training data describes what a realistic image looks like. What most of you have done previously is what is called discriminative modeling, where you take a training sample and then you categorize this into some kind of classification task, for example. So you take your training sample and then you classify it into one class, or you do semantic segmentation or object detection, where you have supervised labels and you try to discriminate the different samples. On the other hand, generative modeling is trying to learn the distribution of the original data. So you're trying to estimate the underlying distribution that lies under your training data. And if you're able to estimate this distribution or this density, you should be able to, first of all, sample from it, but you should also be able to evaluate samples. So by evaluating samples, I mean, given a training sample, what is the probability that this is one existing in your training distribution? Generative models are divided into, or are often divided into two different categories, where we have explicit densities and implicit densities. And this is all based on what assumptions we make about the training distribution or your data distribution. Explicit density can often compute the probability of the distribution, and examples of this is variational autoencoders or autoregressive models. The downside of these, or what is required to achieve this, is often you need to make approximations on the objective function, or you need to do some assumptions on what the underlying function of the distribution is. On the other hand, we have implicit densities. We don't make any assumptions on what the training distribution looks like, but we just assume that we're able to sample from it. And this is the GAN case, and this is what I use in my research. Now, the reason I'm talking about generative models is that, or just covering the different models that we have, is that you need to be aware that there exist different options than GANs. And recently we've seen a large increase in use of energy-based models or diffusion-based models. But the downside of these are often that they have a very long inference time. On the other hand, GANs have a very, very fast inference time, enabling for real-time performance in our task. Generative adversarial networks consist of two neural networks. We have our generator that is taking input some random noise, and this random noise describes what is the content of the image going to be. And when we feed that through the generator, you're going to get something out that hopefully looks realistic. In the start of training, this is going to be completely random noise. To define an objective function to train this generator, we have a discriminator. The task of the discriminator is only to predict if a training sample or generated sample is real or not. So we pass this random noise through the generator, generate a fake sample, and then we feed this into the discriminator that predicts, is this image real or is this image fake? And depending on the decision of the discriminator, you're able to learn the generator through gradient descent. So the discriminator is only there to give feedback to the generator if the sample looked real or not. The discriminator also trains on real samples, so it's aware of what a real sample looks like. Something to note here is that generator never actually sees the original training data, so it only learns how to generate faces based on what the feedback from the discriminator is. In our case, we want to have a conditional GAN where we input this rounding of the face at the same time with this random noise. And this is also fed into the discriminator. Now, this isn't going to be a complete tutorial of GANs, but I'm just showing you the objective function quite quick. The objective function might look a bit scary at the first sight, but essentially what we're doing is just maximizing the output for the discriminator for real samples. So we want the discriminator to predict 1 when it sees a real sample, and then predict 0 when it sees a fake sample. And in this way, we can first train the discriminator through gradient descent, and then we train the generator through gradient descent. So usually you take 1 step of the discriminator and then 1 step of the generator, and they compete against each other and hopefully learns together. In the end of training, the discriminator is usually completely useless, and the generator is the goal of this training process. Going back to GANs, now that we have our objective function, deep privacy again takes in 2 different types of conditional information, feed it through a generator, and then generate a random sample. And then the discriminator sees both fake and real samples at the same time, and then predicts if this looks real or not. This was proposed back in 2014. And in 2014, this was an architecture that didn't really produce very good samples. You can see here on the left-hand side, one of the first faces generated of GANs, and it was a 32 by 32 grayscale image of a crop of a face. And as many of you know, this has really improved the last couple of years. And the interesting thing behind GANs is that a lot of this improvement is basic engineering work. The theory that we have to generate the current samples is mostly the same theory. It hasn't been a breakthrough in kind of theoretical ideas behind GANs, but mostly engineering practices on how to properly train these networks. This has also happened for deep privacy. I released the first version of deep privacy back in 2019 during my master project, and then I released the second version a year later. And you can see here on the left-hand side is the first version, and on the right-hand side is the current version. And we've seen quite an improvement the last couple of years. GANs have some very interesting properties to use for anonymization. And what you're seeing here is an anonymized version of the Prime Minister in Norway. And by using this latent variable that I input to the generator that is describing the content of the image, I'm able to change the identities of the person by just feeding in different random noise. And you can see this is played in real time, so the generator is really fast, able to run at almost 60 FPS. I'm also able to change the pose of the face by just using a slider in this case. And you can see that I'm able to generate quite different looking figures. When we go to the areas of the pose that is not realistic, you also get something that doesn't look realistic. In this case, I placed the mouth way above the eyes. Going back to our use case is again, collect data in the streets of Trondheim and use this data for computer vision research. We had a master's student that looked at this last year, and he took the Pascal VOC dataset, which is an object detection dataset, and trained a model on it, specifically the YOLO5 model. And these are the mean average precision that he achieved. Then he trained the same model, reinitialized it, of course, on the dataset when it was blurred. So using blur anonymization instead of deep privacy. And you can see a quite significant drop in the mean average precision. And for information, higher is better. But if we anonymize it with deep privacy, we're able to almost achieve identical performance as the original dataset. And this reflects that for our use case, deep privacy is almost good enough to use for collecting data and then using the data for computer vision research. Now, there are several limitations of this work. And first of all is the guarantee of anonymization. The human body is, or the identities of individuals is able to be predicted based on other parts of the body. One case is just ear recognition. So ears are a very unique part of the body, and you're able to separate two identical twins based on what their ear looks like. So given if you have a large database of the ears of people and then also high resolution images of them, you should be able to recognize them. This is of course not the case currently, but it is a possibility. The other case is the context and features of the body. So in this case, you probably recognize who it is. And if it's a celebrity, it's easier. But if we start to record in our city at 8 a.m. every morning in the city center, we're most likely able to start to recognize patterns in the data or recognize people at different days at the same time. Another one is gait recognition. The human gait is quite easy to recognize, and it's easy to track people through video data by recognizing gait. This is used in practice currently. And by anonymizing the face, you're not getting away with this problem if you're recording video data. What we believe is the solution to this is human anonymization. So instead of only anonymizing the face, looking at the whole body. We're currently working on a system that is taking the input of dense pose. And dense pose is a system that was proposed by Facebook, which estimates the pose of each person in the scene. And then using this 3D, so this is a 3D description of the pose of the human body, and we can use this to try to generate people. We've made one trial candidate for this during the master thesis of one of our master students, where he took, and I'm going to show you the results here. He took the image of a human, and then he just used the annotation of the pose to generate a mask of that individual. And then he annotated each of the body parts with semantic semantic segmentation. So dense pose outputs the or categorize each part of the human body into different limbs. So you have the head, the torso, and the hand and more body parts. This was all fed into the same neural network that as deep privacy was trained on, and you could see the output right here. Now, this is of course not perfect, and it's work in progress, and it's unpublished work, but I believe this is something that can further improve the privacy of individuals. All of my work is open source, as I mentioned already. You can check out the GitHub repository linked in the start of the slide. You can also test out the system yourself with 2 lines of Python. So you just have to install my repository, and then you can test it out on images. And it should be quite easy to get started with, at least if you have Ubuntu or Linux or Mac. The presentation PDF is also published on my website. And that's all I had today.